Okay, hi everybody. Let me explain the setup for our course module here, course project. This is the Concert SRV02. This is the base module. It has a DC motor, and there's a tachometer attached to this DC motor. There's a digital encoder at here, and there's an analog potentiometer at here. And we also have some gearing at here in transmitting the load. Okay. This is basically for hooking up external add-on modules. You can have a flexible link, flexible joint, double pendulum or single pendulum, inverted pendulum. Okay, so but we're going to basically focus on the base module right here. Okay, there's some wirings from the sensor and also from the amplifier over there. Okay, to this module right here. Okay. The black module over here, that's the power amplifier. Okay, power amplifier. For example, the analog signal from the D and A are given to the power amplifier and then fitted to this base module here to drive the motor. Now this module right here, okay, is an interfacing board. It interfaces between the hardware here with the Tucky board inside the computer. The Tucky board inside the computer will do this, okay, compiling, will do the execution of the code. Okay? Yeah, so that's roughly the system setup here. Okay? Yeah. Now, when you run up the MATLAB, you will see that this Clock RC, which is the library or software for the real-time control system, it will be starting up automatically. Okay. It basically will also add up to the Simulink library, okay, so which you can make use of. Okay. So once you start it up, you can run Simulink. Okay, so as you can see, under the Simulink, there is a Clock RC target. All the relevant library relates to the hardware we're talking about are underneath this Clock RC targets here, right? So you can just drag some of the blocks, make use of them just in case. Now, when you start, make sure that go to your working directory, okay, to the T drive, okay, the thaw space at here. Under the T drive, we have a folder called the ENGR487. And this is the folder basically I want you to work under. You can create a folder under here for your group. And there's the template. So this is the template. Basically the template, you can make use of template to build up your controller. So I'll basically show you what the template is. So here's the MDL, the Simulink file. Okay, so right now it has something here, so I will basically, okay, maybe I'll keep it here. So in the future, in the template, all you have here, just this orange block at here, okay, just the orange block. This orange block represents the model of the system, which is this guy, okay? Yeah. So that model, you can mathematically model that one in one of the short description uploaded to the Blackboard. I have a second order given already. The model is the second order between the position and input, okay? So this guy here represents basically the hardware, right? As you can see, it's a masked block. There's a position. There's a VI, basically that's the voltage input to the module, and the block output's position, velocity, and the actual voltage given to the system. So for this here, the position, they basically enable a selection. The numbers that are here tells you what position signal you are going to use. Are you going to use potentiometer as a sensor, or are you going to use the encoder as a sensor? So if you open it up here, okay, there's another one here for the speed source. So the speed can be from the tachometer. It can also through the derivative of the encoder. So that basically what the number 1 or 2 will represent here. Okay. The VI here, that's basically the control signal into the plant, and that's the control signal going to be generated from your controller. Okay. So underneath block here, that's basically how the signals are being taken in and how the signal is going to be sent out here. So for example, if you look at this one here, okay, and can we zoom in? Yeah, okay, can we zoom in here? So this one here is a HRL read analog time base. So this is basically the block I was talking about under the Simulink. Okay, so if you go to Quark RC data acquisition, generic, time-based. So those are blocks coming out of here. Okay, yeah. Okay, so what this block does is it reads in the analog signal. So there are two analog signals. One is the position, one is the tachometer. So channel 0 gives you potentiometer, channel 2 gives you the tachometer. If you double click here, the board name has to be HIL-1, and this is the channel selection at here. Okay. Similarly, there's a HIL read encoder. There's only one encoder, so that's just channel 0. Okay. So those are basically some calibration gains that are here to calibrate the reading, okay, to give you the correct value. Okay. And by the way, this parameters needs to be initialized. So before you run everything, okay, you need to run this M file here. It's called setup file to initialize all the parameters. Okay. So as you can see from the encoder here, the encoder has two branches. It directly fades out as a position. You can also feed the encoder to a high-pass filter here. So the high-pass filter, which basically it's a butterworth filter, and it does this derivative, give you the velocity estimation for the system. So you can either use this as a velocity or use the tachometer, okay, as a velocity. That's the selection, right? Okay. So as you can see, the speed source number given here. Where's the terminal 2 from? Right, the terminal 2 coming from here, speed source. Okay, that's the terminal 2. Okay. Okay, so that's basically the system looks like, right? Yeah. Inside every one of these Quonset system here, you need to have this module right here called Quark RC. That's initialization module. If you're building your own reading and outputting system, you need this guy here. Okay, and that Quark RC is within this configuration. It's this guy, right? Yeah. So if you double click this thing here, if you double click on it, the board name is HIL-1. The board type is Q4. Okay, so this is our board type. There's also a Q8, but don't select others. It's Q4. That's two important setup here. Okay, yeah. When you run the simulation here, it needs to be set at infinite, and this needs to be simulation mode needs to be set at external. Okay, so that's also important, right? And the last thing is sampling time. You go to simulation, go to configuration parameter. Okay, and here it has to be fixed step. Okay, because it's digital, and then this is the sampling time. Okay, so right now it's 0.001. If you're designing a digital controller, which probably you design based on sampling time 0.01, then that has to be 0.01 change accordingly. Okay? Yeah. So this is the location to change sampling time. Okay. So now what I did is, okay, I just built up a simple feedback module here. In the class we learned, okay, pole placement. So pole placement meaning it's U equal to negative kx vector. X represents the states. So in this particular second order system, and we can pick, if you recall from the assignment, we can pick our states. One is the position, one is the velocity. So here's my states here. So I give it to a mux and give it to the gain. So now in terms of pole placement, generally you need to have a desired pole location first, and then calculate the poles, the feedback gain k, right? But in this case, I'll just arbitrarily plug in a gain matrix k. For example, I'll put a -1 here and 0, right? Yeah. So where exactly did I place the pole? I don't know. So we'll just check it out here. Click OK. Right? So the other thing is here. Make sure this is a matrix multiplication here. Make sure this is a matrix k by u. Okay, not element-wise k times u. Okay. So that's about it. Okay, when you build, you're gonna have this block here. So that's a simple pole placement feedback system. Okay. To run it, okay, so we need to remember we need to run this setup here. Okay, so run the file initialize. Okay, so then coming back here. Okay, so I'm gonna delete this portion here. Quark RC, then build. Okay, so build it. So when you build it, if you go back to your MATLAB window, you will see something's going on to do the compiling and building part. Okay. So there we go. So basically, the compiler will compile or convert the Simulink model into executable file, and at the same time, it will download that onto the target board. Okay, and then the target board will run the executable code and drive the motor. Okay, drive the setup. So that's finished. So now I'm able to run it now. So Quark RC starts here. So it's running. So now here's the system here, because this is a regulator, right? It's not a reference control. Okay? And right now you don't see anything in here. But if I twisted that, okay, and it's supposed to come back, okay. So it should come back here, right? Yeah. So if I twist it, it'll come back. Okay. Probably pull this, run again here. Okay. There we go. So, right? Yeah. So you have this basically disturbance here. But right now it's pretty soft because the gain that we give is only 1, right? It's pretty small. If I give a higher gain at here, let's say if I give a 5 at here, okay? So that'll increase, okay, the response at here. Okay. So let's see. There we go. So if I increase that, there we go, right? So now you see a disturbance being be regulated back to 0. Okay, there is a still slight steady state error because right now there's no integrator included. If you keep increasing the k gain, the steady state error will be decreased. Okay, so that's a simple demonstration of building up a controller. You can easily build up a controller. Okay. Basically outside based on this model right here. Okay, you can base a digital controller. In the future, you can build an optimum controller, common filter plus optimum controller LQG. Right. So those are basically what you're going to do in the as the lecture goes on. Okay, so I think that should be it.
Where do you drag and drop the components from?
All right. So when you if you want to use, if you're building a reference control, you can go to this Simulink library here, go to the common source block, and let's say go to the source at here. I'm gonna probably use a step input. Okay, yeah. So then you can drag the common block here. There we go. Okay. So step input here, okay, right? And now you probably need to have a feedback. Yeah, in terms of the pole placement, there needs to be a gain at here, but that's it. I think you should be. But anyway, if you have a digital PID controller, so I'll just get rid of this. If you're building a digital PID controller, then go to discrete here. Go to difference. Either one of them will do, I think. Go to this discrete transfer function at here. Okay, so in the lecture notes we have in the example of getting a digital controller based on the continuous PID controller, basically using testing or using backward difference numerical approximation, right? So you will basically end up with a discrete transfer function or pulse transfer function. So that basically you can just simply connect this here and this here at the same time, and with the negative feedback, okay, to the position at here, and that has to be negative here. Okay. So that's essentially a simple loop, the digital PID control loop like this, right? This has to be all updated, of course, okay? Yeah. So the sampling time at here also needs to be updated based on what you're using, right? And that's going to be a simple PID, okay? Okay, so this kind of demonstrates the easiness of implementing controller using the Quark RC. If you're interested, you can also use some add-ons for more advanced controls. Okay? Yeah. Thank you.